Hi everybody, I am Dr. Priscilla Jane from the Department of Mathematics. Today we'll discuss about the Laplace transform. Generally, what is a transform? A transform is to change somebody or something completely, especially in a way which improves them or it. But mathematically, what is a transform? A mathematical conversion from one way of thinking to another to make a problem easier to solve. So in mathematics, we use transform to solve a problem easily. What is Laplace used for? The Laplace transform is a very efficient method to solve certain ordinary differential equation or partial differential equation problems. The transform takes a differential equation and turns it into an algebraic equation. If the algebraic equation can be solved, applying the inverse transform gives us our desired solution. So whatever the problem is, the first we apply the transformation and then take the inverse transformation and get the solution of the given problem. So transformation is made here to solve the problem or to find the solution of the problem easily. Now this is a flow chart for problems using transformation, any transformation. So the original problem is transformed using the transformation and the solution is got, and then the inverse of the transformation is taken and the final output is the solution of the original problem given to us. Now, how Laplace transform works? So the problem, the given problem will be in the time domain, which will be transformed using Laplace transform. So it will change, the time domain will change to S domain now. We get the solution using algebraic rules, and then we again take the inverse Laplace transform and get the solution in the time domain. So there are some other transformation also. We use some other transformation also in mathematics. So mainly we use Fourier transforms and Z transforms. So these are the main transforms we use in mathematics. Now this is a very clear flow chart of how Laplace transformation works. So this is the time domain. The given problem will be in the time domain, that is linear differential equation in the time domain. Then Laplace transformation is applied and then we'll get an equation with equation. We use algebra to solve that equation. So we get the Laplace solution, which will be in the S domain. Then using inverse Laplace transform, we get the solution in the time domain. So the given problem will be in the time domain, and then the solution also will be in the time domain. That's why we take Laplace transform and then inverse Laplace transform. Now, the formula to find Laplace transform. The Laplace transform of a function f of t, which is in time domain, is defined as Laplace L of f of t, that is Laplace transform of f of t is equal to f of s. So by this we denote the Laplace transformation of the time domain, which is now changed to S domain. That is f of s equal to integral 0 to infinity f of t e power minus t minus st dt. So we'll take this as equation 1. So this is the formula to find the Laplace transform of a function f of t. The formula to find the inverse Laplace transform is L inverse of f of s equal to f of t equal to 1 by 2 pi j integral sigma minus j infinity to sigma plus j infinity f of s e power ts ds. That is the second equation. These two formulas are very important, and they are the basic or the basement of the Laplace transformation. Without these two formulas, we can't transform. Now, we generally do not use equation 2, that is the inverse formula for inverse Laplace transformation, to take the inverse Laplace. However, this is the formal way to find the inverse. Actually, the formula which we saw earlier, that is equation 2, is the formal way, but it's little difficult for us. It's complicated to do the integration. So, to use equation 2, we need a background in the use of complex variables and the theory of residues. So, fortunately, we can find the inverse Laplace by using partial fraction expansion and recognizing transform pairs. Transform pairs means Laplace transformation and inverse Laplace transformation. They form a pair. So, using partial fraction expansion and transform pairs, we can find the inverse Laplace easily instead of using the formula method. Now, Laplace transform of the unit step function. So, u of t is taken as the unit step. So, Laplace transformation of the unit step, that is L of u of t is equal to, as we know, the formula for Laplace transformation is integral 0 to infinity f of t into e power minus st. But f of t here is the unit step. So, we write 1. So, when we integrate, we'll get minus 1 by s e power minus st, and the limit is from 0 to infinity. So, when we apply the upper limit and the lower limit, we'll get the answer 1 by s. So, the Laplace transform of a unit step is 1 by s. Now, the Laplace transform of a unit impulse. So, an important property of the unit impulse is the shifting or sampling property. The formula is integral t1 to t2 f of t delta of t minus t0 dt is equal to f of t0, where t1 less than t0 less than t2, or it is 0 when t0 less than t1, t0 greater than t2. In particular, if we take f of t is equal to delta of t, then the Laplace transform will be L of delta of t is equal to integral 0 to infinity delta of t e power minus st dt equal to, when we take the integration, we'll get e power minus 0s, which is nothing but 1. Now, an important point to remember, f of t if and only if f of s. So, this is a statement that f of t and f of s are transform pairs. That is time domain and s domain. It means that for each f of t, there is a unique f of s, and for each f of s, there is a unique f of t. Now, building transform pairs, that is L of e power minus t, that is Laplace transformation of e power minus at u of t is equal to integral 0 to infinity e power minus at into e power minus st dt is equal to integral 0 to infinity e power minus s plus a into t dt. So when we integrate them, we'll get minus e power minus st divided by s plus a. So, and the limit is from 0 to infinity. So we get, when we apply the upper and the lower limit, we'll get 1 by s plus a. So L of e power minus at into u of t and 1 by s plus a are is a transform pair. The next one is, next transform pair is L of Laplace transformation of t into u of t is equal to integral 0 to infinity t into e power minus st dt. Here we can see that t is a function of t and e power minus st is a function of t. So it goes under this integral rule, that is integral 0 to infinity u dv. It is in the form of integral 0 to infinity u dv. So we know the formula already, that it is uv minus integral v du. So here we take u as t and dv is nothing but the remaining e power minus st dt. So from u equal to t, we can find du and du equal to dt and v is equal to, we'll get integral e power minus st dt. So here the transformation pair is t u of t and 1 by s square. So again another another transform pair is L of cos omega t equal to integral 0 to infinity e power j omega t plus e power minus j omega t by 2 into e power minus st dt. We know that cos omega t is equal to e power I theta plus e power minus I theta by 2. So we are applying that formula here. Then we'll split into two integrals. And then when we integrate them, we get these two terms. That is 1 by 2 is common outside and 1 by s minus jw minus 1 by s plus jw. When we take the LCM, we'll get the final result as s by s square plus omega square. So this is again a transform pair. Now time shift formula. L of f of t minus a into u of t minus a. So again we set the formula integral a to infinity, because time is shifted. So a to infinity f of t minus a e power minus st. So here t minus a is taken as x. So we have to convert all t minus a to x. So we will be getting x is equal to t minus a and then dx is equal to dt. So t is equal to x plus a. So as these are the limits for t. I think dt is missing there. Sorry. So here x is at t tends to a, x tends to 0, and as t tends to infinity, x tends to infinity. So integral 0 to infinity f of x e power minus s into x plus a dx is equal to e power minus as integral 0 to infinity f of x e power minus x dx. So this is again the formula, time shifting form theorem. L of f of t minus a into u of t minus a is equal to e power minus as into f of s. Next, the frequency shift, that is L of e power minus at into f of t. So again we use the Laplace transform formula, integral 0 to infinity e power minus at and f of t into f of t into e power minus st dt. Here when again e power minus at and e power minus st can be combined and we get e power minus s plus a into t dt, which is equal to, which is same as f of s plus a. So this is also a formula which we have to remember always. L of e power minus at into f of t equal to f of s plus a. So using frequency shift, find the Laplace transform of e power minus at cos omega t. So here f of t is nothing but cos omega t. So f of s will be s by s square plus omega square. We have already derived that. So from that we can write f of s plus a is equal to s plus a by s plus a the whole square plus omega square. So L of e power minus at cos omega t, the formula will be s plus a by s plus a the whole square plus omega square. Time integration. That is L of Laplace transform of integral 0 to infinity f of t dt is equal to integral 0 to infinity and f of t is integral 0 to t f of x dx. And then the Laplace transformation formula we'll have e power minus st dt. Here again we have to use integration by parts and here we'll be taking u is equal to integral 0 to t f of x dx. So this part is u, the part inside the bracket is taken as u, and from that we can write du, which is f of t dt, and the part outside will be dv, which is e power minus st dt, and from that we'll integrate and we'll get v is equal to minus 1 by s e power minus st. So making the making the substitutions and carrying out the integration shows that the answer is 1 by s integral 0 to infinity f of t e power minus st dt, which is 1 by s, and we know this the integral part is nothing but f of s. Now the time differentiation. If the L of f of t is equal to f of s, we want to show that L of d by dt of f of t is equal to s into f of s minus f of 0. So here again we take integration by parts. So u is equal to e power minus st, du is equal to minus s into e power minus st dt, and dv is equal to d by dt of f of t dt equal to d of f of t. So integrating, we'll get v is equal to f of t. So after making the substitutions, we get L of df by dt is equal to f of t e power minus st, and the limit is from 0 to infinity minus integral 0 to infinity f of t into minus s into e power minus st dt. So applying the limits, we get 0 minus f of 0 plus s into integral 0 to infinity f of t e power minus st dt. So finally we get L of d by dt of f of t is equal to s into f of s minus f of 0. So we can extend the previous formula and we can write the formulas for the derivatives. That is the first derivative, the Laplace transformation of the first derivative, L of f dash of t is equal to s into f of s minus f of 0. This we have already derived. So from that we can write the second derivative is L of f double dash of t is equal to s square into f of s minus s into f of 0 minus f dash of 0. So this can be extended to the third derivative. L of f triple dash of t is equal to s cube into f of s minus s square into f of 0 minus s into f dash of 0 minus f double dash of 0. Here you can see a pattern. That is when we want the Laplace transform for f dash of t, we start with s into f of s. For double dash of t, we start with s square and then reduce s and so on. Third derivative, we start with s cube and s square and then s square and then s and so on. And here we always, the first term will be f of s and then f of 0 and then f dash of 0 and f double dash of 0. So in generally we can conclude that L of f nth derivative of f of t is equal to s power n f of s minus n minus 1th derivative, sorry, s power n minus 1 f of into f of 0 minus s power n minus 2 into f dash of 0 and so on minus nth derivative of f of 0. So these are also some important formulas we have to keep in our mind to solve the problems. Now we can see some formulas. These in the left side we have all the f of t's and in the right side we have the Laplace transform of the functions in the left side. That is L of delta of t is 1, L of u of t is 1 by s, L of e power minus st is 1 by s plus a, L of t is 1 by s square, L of t power n is n factorial by s power n plus 1. L of t into e power minus at is 1 by s plus a the whole square. L of t power n into e power minus at is n factorial by s plus a the whole power n plus 1. L of sine omega t is omega by s square plus omega square. L of cos omega t is s by s square plus omega square. L of e power minus at into sine omega t equal to omega by s plus a the whole square plus omega square. L of e power minus at into cos omega t equal to s plus a divided by s plus a the whole square plus omega square. L of sine omega t plus theta is s into sine theta plus omega into cos theta the whole divided by s square plus omega square. L of cos omega t plus theta is s into cos theta minus omega into sine theta divided by s square plus omega square. And there are some more formulas. Please take a note of it. And then I think we'll move to the next slide. So nth derivative, we have already derived. That formula is also here. Now the initial value theorem, which is a very important one. If the function f of t and its first derivative are Laplace transformable and f of t has the Laplace transform f of s and the limit s tends to infinity s into f of s exists, then limit s tends to infinity s into f of s is equal to limit t tends to 0 f of t equal to f of 0. The utility of this theorem lies in not having to take the inverse of f of s in order to find out the initial condition in the time domain. This is particularly useful in circuits and systems. So we have to remember the formula inside the box. That is the initial value theorem. That's why initial value, so it is f of 0. Now, an example for the initial value theorem. So, initial value theorem given f of s is equal to s plus 2 by s plus 1 the whole square plus 5 square, find f of 0. Since we have to find f of 0, we have to use the initial value theorem here. So, the formula f of 0 is equal to limit s tends to infinity s into f of s is equal to limit s tends to infinity. So, the given problem, we write the given problem, given f of s we substitute and then we apply, we take a square common outside and divide all the terms with all the terms in the numerator with s square, as well as all the terms in the denominator with s square, and we can cancel s square and s square, and when we apply s tends to infinity, finally we'll get the answer 1. Then the final value theorem. So because it's final value theorem, it's f of infinity. If the function f of t and its derivative are Laplace transformable, and f of t has the Laplace transform f of s, and the limit s tends to infinity s into f of s exists, then limit s tends to 0 s into f of s equal to limit t tends to infinity f of t equal to f of infinity. So this is the final value theorem. Again, the utility of this theorem lies in not having to take the inverse of f of s in order to find out the final value of f of t in the time domain. This is particularly useful in circuits and systems. Example for final value theorem. So f of s is given. F inverse of s is t into e power minus t cos 3t. So we know this already. So in transform pairs, we have seen this. So for finding f of infinity, we write the formula and then we apply s tends to 0 and get the final value as 0. Now we'll see the real life applications of the Laplace transform in engineering field. So control systems engineering. So Laplace transform is used in the control system engineering. It is used to design proportional integral derivative. PID means proportional integral derivative controllers for cruise control in cars, missile tracking systems, and automated industrial robots, ensuring they respond correctly to input changes. Next, in electrical circuit analysis. So engineers use Laplace transform to solve for currents and voltages in circuit components like capacitors and inductors, particularly in transient analysis. In mechanical engineering, that is in vibrations, Laplace transform is used to model and analyze mass spring damper systems such as automotive suspension systems and structural responses to vibrations. In signal processing and communications, Laplace transform is used to design filters that clean up signals, separating useful communication from noise in communication systems. Next, in process control and modeling, Laplace transform is used to manage chemical concentration dynamics in chemical engineering or to predict the behavior of inverted pendulums. Now, real life applications of the Laplace transform in medicine. It's used in medical imaging and physics. Applied in interpreting data for MRI or CT scans and in calculating the rate of radioactive decay. Finally, we'll discuss some advantages and disadvantages of Laplace transform. So first, some advantages of Laplace transform. The first one is simplifies complex problems. It turns difficult problems, especially involving change over time, into simpler ones. In real life examples, imagine tracking how a car accelerates over time. Instead of dealing with constantly changing speed and acceleration, Laplace transform converts the problem into a simpler form where relationships are easier to analyze. Next, automatically considers starting condition. It naturally includes the system's initial state or starting point. In real life example, if a fan is already spinning when you turn off the power, its initial speed matters. Laplace transform includes that starting speed automatically when predicting how it slows down. Next, simplifies combined effects or interactions. When two effects interact in a complicated way over time, Laplace makes it easier to analyze them together. In real life example, in audio systems, different sound signals combine. Instead of analyzing their interaction in a complex time-based way, Laplace transform lets engineers handle them more easily to improve sound quality. The next is very useful in engineering systems. It is widely used in analyzing systems like electrical circuits, mechanical machines, control systems. When we take real life example, when you press a switch to turn on a light, the electrical response isn't instant. It changes over time. Engineers use Laplace transform to predict how quickly the light reaches full brightness. Next, make accumulation processes easier. Processes that involve gradual buildup or accumulation become simpler to handle. Real life example, filling a water tank. The rate of water flow and total volume change over time. Laplace transform helps model how the tank fills without solving complicated step-by-step calculations. Next, handles sudden changes smoothly. It works very well for systems with sudden changes or shocks. Real life example. When you suddenly apply brakes in a car, the system experiences a sharp change. Laplace transform helps analyze how the braking force affects the motion over time. And finally, helps predict system behavior. It helps determine how a system will behave in the future. For example, in temperature control, like an air conditioner, engine, engineers use it to predict how quickly a room will cool down after switching on the AC. So these are some of the advantages of Laplace transform. Now we'll discuss the disadvantages of Laplace transform. Applicable mainly to linear systems. Laplace transform works best for linear systems and struggles with nonlinear behavior. For example, in real life, many systems are nonlinear, like how a car engine behaves at very high speeds or how the human body responds to medicine. Laplace transform cannot easily model such complex behaviors. The next is not suitable for all time domains. It is mainly designed for systems starting from a specific time, usually beginning. For example, if you want to analyze weather patterns that have been evolving continuously over a long past, that is without a clear starting point, Laplace transform is not the best tool. The next, inverse process can be difficult. While transforming a problem is easy, converting it back to the original form can be complicated. For example, an engineer may simplify a circuit problem using Laplace transform, but getting the final time-based answer, actual voltage or current over time, may involve complex steps and reference tables. The next is requires strong mathematical understanding. It is not very intuitive and needs a solid math background. For example, a beginner trying to analyze a simple electrical circuit may find Laplace transform harder compared to basic methods like direct calculations or simulations. The next, limited use for non-continuous functions. It works best with continuous functions and may struggle with irregular or random data. For example, stock market prices fluctuate unpredictably and are not smooth. Laplace transform is not ideal for analyzing such random variations. The next is not ideal for highly discrete systems. Systems that operate in steps, that is, digital systems, are not well suited. For example, computers process data in discrete steps, zeros and ones. For such systems, other methods like discrete transforms are more appropriate than Laplace. And finally, physical meaning can be less intuitive. The transformed version of a problem may not have a clear physical interpretation. In a real life example, in mechanical systems, time-based motion like position or velocity is easy to visualize, but after applying Laplace transform, the meaning becomes abstract and harder to relate to real motion. So these are some advantages and disadvantages. Hope you all have enjoyed the class. Thank you all.